warming up. Or is it,
Yeah.
I think it needs to warm up. So first of all, I would like to thank Herbert for inviting me and giving me the opportunity to speak here. As the title says already, I'm a physicist, so I'm working on string theory, and hopefully I can convince you that we have found some nice results in string theory which is connected to this workshop. I'm going to report on the following two works. One I wrote with my former PhD student Oliver Schlotterer on multiple multi-zeta values and superstring amplitudes, and there's another project in progress, and I will report some results of this ongoing work. So the talk will be about superstring amplitudes. In fact, we will deal with generalized Euler integrals which integrate to multiple Gaussian hypergeometric functions. Then we will investigate the power series expansions. Actually, this is a power series expansion in alpha prime, which is a parameter in string theory. I will come to this later. And then we will see that this power series expansion is nicely reflected by the decomposition of Motivic multi-zeta values. Moreover, then we see that the coproduct maps this power series expansions to a non-commutative Hopf algebra, and this alpha prime expansion, this power series expansion, captures a Lie algebra structure, and I will comment on this Lie algebra structure, how it is related to the irreducible multi-zeta values and to the Lie algebra of the Galois group. So the picture summarizes both from a physical and mathematical point of view what I want to do. We want to scatter n open strings. So this is an open string, and they just they're scattered, and so they build this so-called string world sheet, which is two-dimensional. And by the tools of string theory, which is conformal field theory, we can map this problem to this upper half plane, or this I mean, it's a disk which then can be mapped to this upper half plane. And we have some positions here along the real axis, which are of course related to this n open strings we are scattering. So in physics we are doing this, while in mathematics we will deal with this complex upper half plane. So in particular we will have to functions on this upper half plane will appear, and actually these functions are these generalized Seilberg integrals, which here again you see this vertex operator positions along, or these positions along this real axis. So they give there's a natural ordering of them, which will be important later. And here we have some polynomials. Actually, we have some real numbers, real parameters, which actually encodes the physical information. I mean, the external momenta of the superstring, and we have some integers. Typically, the integers are between plus minus 2 and plus minus 1 and 0.
Why do you take the absolute value? Does that mean something in the integral? You take the absolute value?
Yeah, because you have an ordering here, so you want here not to cause branchings. But later I will revert this ordering, consider different ordering. So this is not any simplification. And now, so we have an integration of n minus 3 ordered points. Well, this is actually a fact from conformal field theory, that at the end here we only integrate over n minus 3 points rather than n points from the beginning. We can parameterize this ordering in the following way, and then we end up with this so-called generalized Euler integrals. Again, here these parameters here they contain both real numbers plus some integers coming from this map from here to here. But let me point out that because here we have many different sets of integers, there are a priori, depending on the n here, thousands of these functions, and one upshot would of course be to have a basis for this function to get a grip on this, essentially on this superstring amplitude. So let me comment further that you can actually count here the number of Laurent polynomials here. In fact, this is 1 over 2 times n minus 3. So this is a number of polynomials, and actually this agrees with some physical input, which is a number of kinematic invariants. So these are the number of scalar products you can built for independent scalar products for n vectors. Furthermore, these integrals are integrals on the moduli space of Riemann spheres with n marked points. And as I said, fortunately, there's a basis of n minus 3 factorial and of dimension n minus 3 factorial, which to which you can boil down any function. So given a certain set of these integers, you get lots of different functions, but fortunately you can express all them in terms of this basis. Just two examples. I mean, they look pretty trivial here. So this is 4-point scattering. You end up with this Euler beta function, while for 5-point scattering you end up with this 3f2 hypergeometric function. Of course, now you might think that for 6-point and so on, you just get 4f3 and so on, but actually it is going to be more complicated due to this number of Laurent polynomial in the integrand. So here's just the case for 7 points. Remember, we have n minus 3 integrations, so we have 4 integrations. There's these polynomials, and this is the physical input. These are these kinematic invariants, our parameters. I mean, we have 14 of them. As I said, the number of them is the same as the number of polynomials. And now, what we want to do in physics is, remember, there's these parameters here. They depend on this parameter I introduced at the beginning, alpha prime. Alpha prime is the string tension. So when you send alpha prime to 0, you get back point particle physics. So in this case, you get back Yang-Mills theory, while alpha prime non-zero means including fully string effects. In other words, including all these effects from this extended string worldsheet. So in string theory, we are particularly interested in getting power series expansions with respect to alpha prime to 0 of our amplitude. In other words, of power series expansions of this integral. This can be now, so now we expand this integral with respect to these parameters here, so we assume them to be smaller. And so strictly speaking, what we are doing, we take all these s's to s times epsilon, and si goes to epsilon times si, and we expand with respect to epsilon, the same with the t. And so, of course, the lowest term in this case is particularly simple because you don't have poles here. So you just grab this polynomial here, and then this you have to compute this integral, and then this gives you the lowest term here. And the next term is linear here, and you have to compute these integrals. And of course, here, this is now the first instance where you see that my talk or superstring amplitudes have to do something with theta functions and actually also with multi-theta values. Let me just phrase this more generally. So we consider this generalized Seeberg integrals, which are integrals on over n minus 3 points. And there's a theorem by Terrasoma and Francis Brown that when you expand this with respect to this integer, with respect to these real numbers, you always get multi-theta values, combinations of multi-theta values in Q. So that means, for example, looking at these two examples, the lowest terms here are some theta functions, and of course then it starts depending on this parameters here. However, what you see here, there are two crucial differences between these two integrals, and actually this is not what this theorem tells us. So the theorem tells us that we should expect here some Q expansion in multi-theta values, but it doesn't tell us this difference here. So the difference here is that here you have a mixture of theta functions of different degree, while here it's a fixed degree. I mean, it's just degree 4. And in superstring theory, actually from superstring theory, by writing these integrals graphically, actually we found a dictionary when to decide by just looking at these polynomials whether we should expect some I call it in physics non-transcendental power series or transcendental power series. So I apologize to call it this way. So yeah, weight mixing I call non-transcendental power series, and no weight mixing I call transcendental power series. I apologize because I gave this topic in front of Sasha Goncharov and he didn't like this notation. And yeah, so this I call non-transcendental power series, while this is a transcendental power series.
The second is rational, the first is transcendental.
Well, yeah, I just mean let's say mixed power series and non-mixed power weight mixing. Yeah.
Could you explain what the criterion is on the graph?
Yeah, the criterion seems to be that whenever you have such a closed loop, you have this mixture, while when you have a pure graph without loop, I mean a tree graph, you don't get a mixture.
Is that an interpretation in terms of the pole filtration?
Interpretation in terms
well,
of
you have a pole filtration. Well, I'll ask you after this.
Mm-hmm.
So it's not connected to the fact that the first graph is disconnected.
No, doesn't matter. I mean, you might even have here, I mean, when you have more points, some disconnected trees. So the crucial point is that you have a loop here. You have a non-tree. This is the difference. So now let's come back what we considered so far. We have considered these ordered integrals over some Laurent polynomials, the Hilbert integrals, and we had many of them actually, and then we found that we have, for a given ordering, we have a basis of n minus 3 factorial for just one given ordering. But of course now you can do something different. You can consider here different orderings along, so different orderings, how you order your points along the real axis, where you integrate, and then you get another n minus 3 factorial basis for this ordering. So you have essentially a basis of n minus 3 factorial times n minus 3 factorial hypergeometric functions. So keep in mind this ordering means this n minus 3 factorial is the basis of these different orderings here, while this is the basis of the different polynomials you have here. I mean the basis, the dimension of the basis. So you can put them into a matrix, and this matrix is then the period matrix of the underlying moduli space of Riemann spheres with n marked points, and it happens that you can compute the Euler number of this and precisely find n minus 3 factorial as Sasha has told me. So, and this F will now be the main subject of what I'm going to talk in the following. So, before let me just go back how this is related to the amplitude, let's say to the real amplitude you measure at LHC, for example. So we have this mathematical object, this period matrix F, and if you want to go back to physics, you just need to multiply a vector here, a physical vector, which encodes the so-called Young-Mills basis. So this is just captures all the kinematical factors and so on, and then you get the full string amplitude. But in the following, we will focus on this period matrix F here. And now let's just look at the 5-point case. You have already seen that in 5-point case we have these are of course then 2 by 2 matrices, and then we deal with 3 F2 hypergeometric functions. So this is a choice of basis. So you get this, and have no poles, so you can expand them. And actually, what we did is that we expand them to very high orders, thanks also to the great work of what is in the data domain, David Broadhurst and Jos van Marzelen and Blümlein. So I will come to this, but let me just make 2 slides, which I guess are unnecessary for this audience, but just to tell you my notation. So we will deal with multi-zeta values, and this is my notation. This is called the weight. I mean, the weight is the number of these integers, and I mean, physicists call this also transcendental degree.
Some physicists.
Some physicists, yeah. I think it was Kotikov, Lipatov invented it. I picked in the literature. And R is called the depth, and there's this Kontsevich relation, how you can interpret these multi-zeta values in terms of these iterated integrals. Furthermore, you can choose there's the famous conjecture by Sargier that the dimension of this graded algebra for each n is given by this number, and You can choose a certain basis. Here I put a certain basis. Of course, this is, for example, the weight 12 case. Of course, I was motivated by the data from the data mine. So by that, for example, you can express this guy in terms of the basis written here. So I don't want to talk more on this, which are trivialities for most of the audience. Now let me tell you our findings. So the finding is that this period matrix F, first of all, decomposes into the product of 3 other matrices. So there's this exponential which only contains single zeta functions, and there's a matrix, of course, n minus 3 factorial times n minus 3 factorial, which, well, physically, I mean, which of course, is defined by this way. So it's just the zeta 2n plus 1 part of this whole object. Then there's a matrix P which contains all zeta powers of zeta 2. And then there's Q, which, so to say, contains the rest. In particular, it contains all multi-zeta values.
All multi-zeta includes all zetas and powers of zeta 2. So
yeah, I mean, sorry, I mean multi-zeta values of that greater than 1.
and what do the 2 double dots mean?
The 2 double dots means that, strictly speaking, we have some ordering here. So when you, for example, get the zeta 3, when you want to extract the zeta 3, zeta 5 part of this exponential, you should take this term and not the other way around. So what you could, of course, also do, you could just write the exponential, this exponential without dots, by like this, and then you have here the higher weight guys.
Okay, so that's all you mean. So it's just
Yeah, that's all what I mean.
product of the individual.
Yeah, that's all what I mean.
You're trying to get rid of the products.
No, but that's completely different. I mean, that's not in any reasonable sense the same as the exponential of the sum for non-converted values. I'll for example, and this is a much simpler formula, and it's correct.
Yeah.
So why are you writing the wrong formula? I mean, you can't take the log of the product exponential.
Well, it's not wrong as long as I have not. I mean, let's say what you call wrong is.
There's no operation called dot, which will send this to the other. It's only when you have the thing written on the board that you say you mean by the simplest map. But I don't think there's any linear map that you can. I mean, you can't sum zeta 2n plus 1 times n 2n plus 1, do anything with it, and extract this by any universal.
So you say it's
I
better.
think you should just write, and it's no longer that it's shorter, just product e to the that, and then it's correct. And
Okay,
it's
good. Yeah, and thank you.
I mean, if that's what you mean, that's.
Yeah, I only mean this. Of course, it's a crucial point that these m's are non-commutative.
Yeah, so it exactly doesn't only depend on the sum, but it's simply this.
Yeah. Okay, now let me just show you how this Q looks like. So the Q starts with 1 and then the first term are this zeta 3,5 at weight 8, and so you have lots of commutators here. And when I give this talk in front of physicists, I always have to apologize for these strange numbers here. But here I think, like for example, this combination here should pretty much remember you to something.
It reminds us of something.
Yes, so so the form is in principle nice, but anyhow, what we will see that this form is also bolstered, or it's just the same form what you get by looking at the composition of motivic multi-zeta values. And now, just an example for this 2-dimensional 2x2 matrices case, which comes from the expanding 3F2. This is just what the P2 is. So it's from this matrix P. It's a first non-trivial term. So P starts with 1 and then comes. So it's just a zeta 2 term. So as I said. This piece, I mean, these matrices must contain somehow the physical information, so they contain all these scalar products of external momenta, and we have 5 for the 5-point case, and the M3, which is this object in the exponential describing the zeta 3 part, is then this matrix here. So the dimension of the polynomial is agrees with the dimension of.
Excuse me, could you explain the notation? Because you have Sij with 2 indices and you have SI as well.
Okay,
That's
sorry,
fine.
I missed it. Yeah. Okay, this is here. This is for the single SI and SI chase.
Adjacent.
It's just alpha prime ki times k chase.
With a single index, what does it mean?
The single index is chi I plus
Adjacent ones at the bottom.
It's the adjacent one.
yeah the
Right.
adjacent one.
Oh, so it's just the special case. It's just I had this one.
Yeah, it's a special case from the other one. Yeah, it's I mean, the point is that you have only 5 independent. These are the 5 independent guys, and all others. I mean, these ones all can be expressed in terms of 5, because you have from this scalar product you can build with this 5 momenta. You have only 5 independent scalar products, and so it's essentially only a short notation for writing longer terms. So of course now you can extract physical, for example, physical informations at weight 10. Then you get this nice expression that they are given in terms of this form. And actually we'll come back to this in a moment when we.
But in general, this wouldn't be well defined because it depends on choice of basis.
Yes,
You
of
can't
course, yes,
talk
yes,
about-
yes,
so
yes.
this isn't quite a well-defined process. So
Yes, so far it's this is my next slide. It's so to say it's completely basis dependent. So let me just say, okay, nevertheless, I find Q has some intriguing intrinsic form. Namely, for example, you see that this multi-zeta values of depth greater than 1 are always accompanied with this commutator structure, and you can also go to a minimal depth representation by introducing Euler sums. In fact, what we also found, and which is proven now, what in our next paper, up to weight 21, that you can actually write this Q in terms of an exponential. Okay, sorry, I have to double check. Again, here you should not write it as a sum of terms in the exponential. Again, you should write it as individual exponentials.
and again from right to left.
Yes. Sorry, yeah. But of course, as you pointed out, this is whole basis dependent. You might just do this little change, and then the form of Q changes completely, or you might better like the Hoffman basis, and then of course the structure will also completely different. And however, when we go to the coproduct structure, this will completely remove all this ambiguity, and we will have something very nice, which is completely independent of the basis. So let me just briefly review what we are going to do now. Is so we introduce motivic multi-zeta values. So the problem is, or one reason to go to motivic multi-zeta values is that you want to, for a given for any multi-zeta value, you want to find the decomposition with respect to a basis. So you want to determine these coefficients in Q, and so to explicitly describe the structure of this algebra, this motivic multi-zeta values are replaced. The ordinary zeta functions are replaced by the motivic objects. By this graded algebra is mapped to this Hopf algebra, the graded Hopf algebra.
Maybe the other way.
Yes.
H maps to Z. You can't map Z to H.
Yeah, because it's
Which is- I mean, nobody knows whether zeta 3 squared is not the same as a multiple of zeta 6. Because it's only surjective. No, now you've written it correctly. H goes to Z, but before you wrote Z goes to H.
Yeah.
You don't know if there is such a map.
Okay.
Which is
Yeah.
actually very cool.
So the motivic zeta functions you introduce by the iterated integral. So I showed you this relation, the Motivic relation between ordinary zeta functions and iterated integrals, and then you do the same for the motivic objects. What is nice here is, of course, and what will also reflected by the superstring amplitude, that this Hopf algebra splits into a part which captures this powers in zeta 2, and another part which is where you divide out, which is defined mod the zeta 2 part. However, to actually compute, for example, these coefficients for a given decomposition, or to really do actual computations, you further map this Hopf algebra to some algebra co-module, which has been introduced by Francis Brauner. So you introduce this co-module, which is generated by this symbol f, f by all these odd symbols tensoring this f2 part. And this is the object where you want to do actual computations, where you want to decompose certain zeta functions, Motivic zeta functions. So you have to define how you have to define this map. This map is defined by giving the map for all single zeta functions. So the single zeta functions of odd n are mapped to these words here, or these letters. And but it takes some time to really compute this map for any zeta function, multi-zeta function of for example, weight n plus 1. This is done through the coproduct, actually to some smaller subset or derivation of the coproduct. I don't want to go into detail with, but let me just state that by this map we can send any Motivic multi-zeta value to some polynomial, non-commutative polynomial in this little f. So here's just an example which I took from the paper by Francis Brown. So at weight 10 we can, for example, choose this basis for the Motivic zeta function. We get these objects here, and now what we can do now is, for example, we want to get the decomposition for any multi-zeta function. We compute its image in this non-commutative co-module, and then so we get a polynomial. According to this rule, we get a polynomial in f, and then we can try to match it with this basis, or of course we could choose another basis, but we can now try to match it with this basis. This is conveniently done by the Motivic derivation or the Motivic decomposition operator. So you essentially invert this map, and then you get this operator here. So this operator here now acts on the image of a given zeta function at weight 10. So it is a polynomial in the fi's, and then these operators act on this, and then you just have to only compute these coefficients here, and then by that you get the decomposition. So this is just from the from the paper by Francis Brauner, but when you look at these numbers here in this commutator structure, and when you compare what I have shown you at weight 10 for the superstring amplitude, you see that, for example, the zeta 5 squared term comes or brings precisely the same structure here. So you have this 1 over 2 m5 squared times 3 over 14 m3, and maybe you also could remember this 1 over 14 for the 3/7 part. And so we see that this is precisely the same structure at weight 10, that this commutator structure and even also these rational numbers precisely match what we get from completely different directions, namely from power series expanding multiple hypergeometric functions. So the map is, or the dictionary is, that you should replace this Motivic derivation operators with our matrices, and then this coefficient. This takes the f2 coefficient in this co-algebra, in this co-module, and this should be replaced with the zeta 2 part. The matrices describing the zeta 2 part. So by that you can just map the Motivic decomposition operator to the alpha prime, or to the power series expansion of our superstring amplitude. So in order that, of course, we compared it at that time. Unfortunately, it was only computed by Francis Brown in his paper up to weight 10, the decomposition operator. So we computed further up to weight 16 all these phi maps and the decomposition operators, and we got precise agreement up to weight 16. For the paper we wrote last year, and now we have it up to weight 21. So I think this should tell us the following: that this motivic multi-zeta values and their decomposition they encapsulate the alpha prime expansion. Or of course, you may also say vice versa, that the alpha prime expansion somehow knows about this motivic decomposition. I mean, alpha prime expansion, this is a physical, what you want in physics, a power series expansion. Now, there comes back this comes back to the question of Professor Salgier, that this is all completely basis dependent. Of course, also these motivic decomposition operators you can also introduce for the Hofmann basis, and then you get different coefficients, you get different rational numbers, and so on. But now what we do is, so let's just go at weight 8. What we have in the superstring amplitude, we have, for example, this contribution. So let's collect all contributions depending on M5 times M3. So we can then apply this map phi, which maps the Hopf algebra. So the Hopf algebra of motivic multi-zeta values to the comodules. This was the script U, and then so this motivic zeta functions are mapped to this little f's, and then we get this symmetric combination. And we can do it, of course, also for all other terms and for higher terms. And by that, the map, this phi map of this motivic period matrix is given by this nice object. So all ambiguities here, all rational numbers and so on are completely have completely trivialized. So it's just the coefficients are just 1. So this is the motivic period matrix. Takes a simple structure in terms of this Hopf algebra. And in fact, I mean, Oliver gave this talk, or talked about this work in Paris, and then he told me that there was a remark by Professor Salgier that one should better write this in terms of a geometric series with some prescript.
There should be a transpose somewhere, because in your first product, the f's are multiplied in one order and the m's in the opposite order. So you should put in the formula that you quote from you should, for instance, put m transpose and then transpose the whole thing, just to get the order correct.
Yeah, this is I meant by the prime here.
There's no operation on summation. That doesn't make sense. Mm-hmm. Actually, your m's have been transposed from the beginning. All of the formulas would have been easier. If you just put m transpose and transpose.
And transpose the whole thing.
Yeah. Okay. Yeah.
Mathematical notation.
Mm-hmm.
And that's not a very deep comment. This was a trivial restatement you had written.
Sorry?
This is just a trivial restatement of the others.
Yeah, sure, of course, it's just rewriting this in terms of the series, geometric series. And so this is that was the result of the first paper with Oliver Schlotterer. That
again, sorry, can you remind us? P2K is itself a multi-zeta thing, or it's no?
No, it's just a matrix. It's just a matrix encoding such polynomials in the S.
But it's not known explicitly. So this is
no, you can. I've shown you actually P2 for.
Well, the first few terms, but I mean, is there closed form? Is that something simpler? Completely forgotten because it's many slides ago. It's something explicit because it's just the zeta 2 part.
It's yeah, right. Well, in the project we are doing at the moment, we are getting some some control of how to write down a general formula. I mean, it's true that it is. I mean, we have constructed it up to weight 20. I mean, P20. So to say, that means up to P20. But then, of course, the natural question was: can we write? Can we get a general formula telling us what it is at higher weights? And we have some work on this. So now let me come back to this algebra structure in this power series of this multiple zeta values. So we have seen this commutator structure, and we can introduce this Lie algebra over Q, this graded Lie algebra, which is generated by this symbols M. I mean, these odd symbols, and with the Lie bracket, then we get this. We generate this at a given order at a given weight. So let me just show you graphically what we have found. So we have here I show you the linear independent terms in the alpha prime expansion. I mean, of course, this starts to become interesting at let's say at here. So these are the objects in this Q. I mean, so that the Q was a part of the alpha prime or the power series expansion, and here's the dimension of this algebra, of this graded algebra, and this is the weight, and that is the number of irreducible multi-zeta values we find at this particular ordering. Of course, the next slide might become more interesting because this is what we have at weight 20. So we have this, we have 13 different commutator structures of this algebra, and this is precisely also the number of this irreducible multi-zeta values appearing at weight 20.
Is it the case that double commutators vanish? Double commutators?
I will come to this point. I will
okay,
come to
so
this point.
matter.
Yeah, this is a very good question. By looking at this table, it seems that there's a relation to another algebra which has been studied by Ihara to relate the Galois algebra of the Galois group to a more this more tractable object F. And this F is a free-graded Lie algebra, and it has the generators. You have the same commutator structure, and actually there's a nice formula in the paper by Tsunogai which computes this dimension. And by comparing this dimension formula, it is precisely the same dimension what we find up to weight 20 for this algebra. For this
What was FM again?
FM is this algebra which has been, I think, invented by Ihara.
But that's just my conjectural formula for the dimension. That the dimensions agree. That's the old form. That's the old conjecture.
Yeah.
But the dimensions agree at these two things: the multi-zetas and that. That's my conjecture. 1/1 minus x squared minus.
Yeah, but our conjecture is that the dimension of what we find in the superstring expansion at alpha prime to the m, that this objects here actually
No, these are just the bracket sum symbols of weight 3, 5, 7, and so on. And whether they come from, I don't understand about the dimension. Surely that's, you know this very well. I mean, if you just take symbols, now it's not superstrings anymore, they're just symbols of weight 3, 5, 7, and you take all possible Lie brackets, and of course the number of them is just the conjectural dimension. That's what the pi squared form, right? That is the conjectural dimension form.
Yeah, but these are matrices which depend on this how many external string states you have. So
It has to be. It's some quotient of this 3D algebra, because there aren't enough. If you estimate the number of possible polynomials in the SIs, it grows far too slowly.
No, of course.
So something like a metabillion quotient.
No, but I mean,
of
what's
the
on the
higher
left here we know is the same dimensions. What's on the right? Just all possible monomials in the ends. In the symbols m, it's just the right number. I mean,
I agree that if you replace this m's in terms of this taus, in terms of this free-graded Lie algebra, it agrees, but we do not know whether this our algebra in terms of the m's is freely generated.
It can't be.
Yeah, and we have counterexamples.
but why should it be freely generated?
Well, I mean, the
formulas only involve the projection of it. Everything you get is a polynomial in the end, in the brackets of the ends. That's what you showed us. So the number of possible terms is just the same as if they were pre-generated. So the number of possible commutators you can have.
Yeah, but due to these relations here, for example, for the 5-point case, you get starting at weight 18, you get fewer terms. You get fewer commutator structures because they are the same. So here, I mean, there's, for example, you can take 3, 5 and 3, 7, and then you have at weight 18, you have for the 5-point case, you have.
So what you get by expanding in the slope parameter is a more special, more rigid structure.
We get one at this point, at this level, we get one less. For the 5-point case, while for the 6-point case and higher ends, we get the fully fledged expressions. But there seems to be a dependence on this n, so on the dimension of matrices.
Is it reasonable to assume that if n goes very high, then
Yeah, precisely. Yes.
so
yes.
this will reduce to free algebra?
Yes, precisely. That is.
Okay, that's what my next question was.
Yes.
Yeah, that is the belief that when n goes to high values, that we can again then really match it to this freely generated algebra, and that's a match. But
That's a theorem, I think, because that must be a theorem because we can write a basis. We can realize any Motivic multiple zeta value as a period of a moduli space with sufficiently large n.
Okay, can we talk about
I
that?
agree.
Mhm. And of course, I mean, this is known to you. I mean, that is there's this relation also that this which Professor Sagis stated also now that there's a relation to the irreducible primitive multi-zeta value. So of course, that dimension is the same as this this auxiliary algebra you introduced to describe the Galois group. But let me just make this point that for us, I mean, this depends on the dimension. This algebra generated by the m's depend on the dimension on this external n, and we, as I said, we do find agreement as soon as the n, the dimension of the matrices is higher. Like for example, for the 6-point case, you find all these independent commutators. And let me just go back to this, what we found in this, by just doing this power series expanding of the multiple Gaussian hypergeometric function. This you have already seen, but actually this is, when you go higher, it starts to be, to stay nicer. And of course this must be like that, since we have already seen that it matches this Motivic decomposition operators, but you see that, for example, at weight 20 we find this combination, and here there's no ambiguity because they are independent even for the 5-point case, just for 2x2 matrices, and this of course should remind us to what is known from the stable derivation algebra and the filtration. So, for example, there's this relation which is somehow resembled in this combination. Are there further questions on this so far?
Could I ask a question?
Mm-hmm.
So you're saying that you get some double commutator quotient of the Hara algebra. That means you're getting a subspace of the space of all multiple zeta values. Can you characterize? Do you have an expectation for what kind of multiple zeta values you get coming from the superstring amplitude? Are you just saying it's some depth? It is just related to the depth, or is it something more?
I mean, no, we get all of them. I mean, it's not no dots. I mean, there's all of them, which I mean, like as I showed in the table.
You will not get all multiple zeta values.
No, we do get all.
For n equals 5.
No, we get all.
So you said if n is too small, you have this
No,
extra.
it's dimension.
Yeah, we don't get the commutator structures, but we do get, for example, at weight 20, we get all of them, for sure.
You're saying there exists a linear combination where the coefficient is 0.
Yes.
I mean, here, you, for example, starting at weight 18, you
Yeah.
have a relation between, I think, the last two guys, subject to this double commutator, and then so also here you have all guys appearing, all 18s.
I'm saying that you have a Lie algebra which is dual. The Lie algebra is the thing on the left, and dual to it is the Motivic MZV, which is dual. So if you're working a quotient on the left, that means you're in a subspace on the
Yeah,
right.
of course. You
My
can't
question
get
is,
them
so
all.
what is there a natural way to characterize this subspace? Do you have a guess?
What you're saying. If it's a smaller dimension, if there's one relation on the left, I mean, if one thing vanishes, you don't get everything on the right. You may see each of those basis elements occurring somewhere, but
Okay, I get
you will get a
then.
subspace of
Okay,
what-
then I get some linear combinations of this.
Yeah, my
The
question is, so
subspace,
do you have a
it's
guess
asking if
for
you know
what
what the
that
subspace
is?
If you identified the subspace in this question, you certainly get a subspace.
Yeah, I agree.
And do you know what it is his question.
No, I don't.
Say in weight 18, can you recognize which?
No, I mean,
It's
I would like to
seven-dimensional
know
subspace.
how one
What
can
is it?
determine the subspace. but I thought the question was whether these guys do appear, and they do appear, but of course they might appear in a certain linear combination.
No, they have to. I mean, only 7 linear combinations of these 8 numbers will appear. It's 1 dimension less. So of course, each individual may show up in those 7 bases.
Okay, so now are there further questions? I just want to show you some final aspect of this multi-zeta values in connection with this hypergeometric functions, which I did recently with Tom Taylor, and actually this shows another nice structure how these multi-zeta values appear. So you can investigate Mellin transformations on this, more precisely inverse Mellin transformations on this multiple hypergeometric functions. So I think everybody knows what Mellin transformations are. This is a single variable Mellin transformations, and what we have to do is, or what we are doing is, just take a simple example. This was this four-point scattering case we just described by the Euler beta function, this quotient here. And now we do a double Mellin transformation on this variables x and y, and we find this object here. In fact, I mean, dealing with this thing, you have to extend the concept of this Mellin transformation to distributions and other singular functions, which has been mainly done by Kang in the 50s. However, it is quite, or at least for us, it is quite strange, because here we know that when you expand this in terms of small s's and u, you get the power series and with coefficients of single zeta function in that case. And now expanding this, you should also find zeta functions. And of course you can.
What is theta? Did you tell us?
It's a heavy side step function. Yeah, just trivial, and this is a delta function. So on the left-hand side is of course what you should expect, and when you expand this, or what you get when you expand this gamma function. On the right-hand side, it is written what you get by expanding this singular functions. I mean, delta function times this step functions, and in fact there must be this zeta 2 here. So for me, this is quite mysterious how by expanding this singular functions, this zeta functions appear. And now you can generalize it actually by.
But you don't mean these functions are equal. You mean the Mellin transform to one on the left is one.
If you do
you wrote an equal sign, you mean that thing's Mellin transform.
This is equal, yeah.
Yeah, but that can't be. You mean they're different variables. I think you mean the Mellin transform.
I mean subject to the transformation. Or if I do a Mellin transformation on this, I get a.
Yeah, but the function's not equal to its Mellin transform. I think you mean
sorry.
the left-hand side is Mellin
of
transform.
course,
Right
sorry.
side. Okay. It's
Yeah,
MF,
it's the same.
It's MF of that whole thing.
Yeah. Sorry, yeah. Of course, yeah. So you can extend it in effect how you do this Mellin transformations. You introduce, you have already seen this number, you introduce these dihedral coordinates, and by that you can do m-dimensional inverse Mellin transformation on this multiple hypergeometric functions, and you will simply find this product of delta functions, and at times this heavy side step functions. So this is of course from the physical point of view quite striking, because in physics what we actually found in this work is that by that you can essentially describe open superstring amplitudes, so encoding fully fledged string theory by just pure supergraviton amplitudes. So you completely trivialize the so-called Cooper-Nielsen factors, or the contribution from the heavy string state. However, what is mysterious to me is that, so for the higher end case, I mean not for this case, we have this multi-zeta values, and of course even the single zeta values. It is quite mysterious to me that then from expanding this you get all these multi-zeta values, and so I want to end here.
I have a very naive question from a non-string theorist. If you look at the closed superstring amplitude, can you write down, are there closed integral formulae for this in the case n equals 5? for 5 points?
You mean for the Mellin, or
No, the previous story. But
you mean a
said the
closed
open
formula for this map and for the finite?
The closed superstring. So I'm not asking about the open superstring amplitude, but the closed superstring amplitude, which you didn't mention. Do you have integral formulas like you wrote down on your first slide for the open superstring amplitude?
Okay, yeah, you have, of course, that is the starting point. You have integrals over the complex plane.
Yes.
And then the way how we compute them in string theory, or what we have learned how to compute it, is that you do it by an analytic continuation, and it essentially boils down to a product of two open string amplitudes, or two real integrals times some sign factors from the monodromies.
Thank you. Okay.
And then by that, I mean, so to say, we are back at this problem. And actually by that, in our paper with Oliver from last year, we took all this result, like here for the open string sector, and then we applied this the famous KLT, Carré-Level-Tie relation, and then found results on the zeta function structure for the closed string case.
Is that passage explicit, or is it some algorithm? Is there a closed formula for such a thing coming from string theory? That would be very
Yeah, there is. Well, the closed, I can. I mean, you have n minus 3 factorial terms again. So and actually n minus 3 factorial squared. But basically, it's a closed formula. Yeah. I mean, I can give you the reference. More questions?
I like this work very much, and I remark, you may know already, that there's a very, very similar problem in quantum field theory, and that is dealing with subdivergences in diagrams, which have the effect of changing a massless propagator to 1 upon p squared to 1 upon p squared plus a multiple of epsilon in dimensional regularization, of dressing a canonical Feynman diagram with propagators which have some expansion in epsilon. Of course, when you make that expansion in epsilon, you get logarithms in the numerator.
Precisely.
I set the challenge about 10 years ago of showing that the central tetrahedral diagram, which when you cut it as a two-point function, always yields multiple zeta values, and that challenge was met by, I think, Stephan Stieberger and Isabella Beerenboim. But Francis has progressed far beyond that at present. Is that right? Would you like to report on what types of Feynman diagrams, when you
I think
include the subdivergences?
Probably up to 6 loops.
Up to 6 loops.
Or maybe one exception, probably not.
And my little contribution to this subject, if you look at it before this real breakthrough, is a paper called "Where Do All the Trivial Products of Multiple Zeta Values Appear From?" I agreed to have it published only if the editor would include the word trivial, and it comes from a form of pseudo exponentiation, just like you're talking about. So if you look in the archive for a paper by me with the word trivial, and look
You have only one, maybe.
tedious. Sorry, tedious.
Yes.
Thank you. I forget tedious. But there is that pseudo exponentiation. It's a comparable problem. Of course, everything that I said in my talk on Monday about these very special numbers zeta 353 minus zeta 3 times zeta 53 are about the Feynman diagrams with no subdivergences. These are the periods that Oliver will be talking about. I want it to be noted that when you put in the subdivergences, you start to see the full multiple zeta values and not the restricted periods I was talking about. And the same thing, I think, is the same thing is happening in your expansion in alpha primed. It's just that you have to go to sufficiently large number of external legs before you populate the whole space.
Yes.
Well, thanks again.